Okay. So content, use FSP files. Basically, what are the necessary files you need to have in your build? Use UPD for FSP configuration. What is the implementation coreboot to be able to use UPD? And then I'm gonna quickly walk through FSP phases and then talk about what needs to be done in terms of integration for auto-phase to be successfully executed. Then I'll talk about a few specific things that I learned from the project. And also there's some issues I will talk about that we found from using FSP from Skylake. So and then I have a picture of memory map of Skylake using FSP, and then we'll do some QA if we have time. So use FSP files. So before that, Skylake FSP complies to FSP architecture version 1.1. The newer version is FS 2.0, as Giri talked about yesterday, and then NJ talked about the first day. So starting Apollo Lake, they're using FS 2.0, but Braswell and Skylake are using FSP 1.1. But I'm talking about the Skylake, so it's 1.1 here. But a lot of the integration mechanism actually applies to 2.0 as well. So needed file in your coreboot build. There are two files that you must have. FSP.fd is the FSP binary. FSP-UPD VPD.h is the the header file that you have to have, and which contains the VPD-UPD data structures and then related definitions. The FSP BSF file is not required for the build, but it's for you to use the BCT2 and config the binary, some static values. Enable FSP usage. There are a few config flags you need to worry about and config in the build. At least on those here. So config FSP file, the first one actually will have the path to the binary. Config FSP include path will have the path to the FSP UPD VPD.h. And there's the FSP location, the FSP cache size. You have to specify that. Of course, config have FSP bin. And then use FSP 1.1, you have to set yes to those two. FSP integration guide is a document that's part of the FSP download package from Intel. You want to read the document to understand the generic bootloader requirement for integration, not specific to coreboot, but it's a general bootloader. And then some SoC, and then the SoC configuration definitions. Basically, it will tell you what all the UPDs are doing and what those options are, and what values you can set those values or those options to. Use UPD. FSP UPD's interface, as you might know already, for bootloader to apply SoC configurations to FSP in phases in order to support your platform. UPD do have default, so you want to refer to integration guide for those default values. If you like the default, okay, you probably don't want to touch it. How we implement in coreboot to use UPD, for FSP to consume. We use existing coreboot framework to do that, right? So chip.h will supply the SoC configurations, which maps to the FSP UPDs. If you look at the chip.h under SoC Skylake, there's a big list of configurations that's actually mapping to the FSP UPDs. I have an example there. And where do you config those items? Device tree.cb, of course. So that's where the configuration are actually valued per board requirement. One example is the Google large device tree.cb, and that's where you register. For example, you register enable Zadia equal 1. So that's where you set the value that you want for your platform. But this is not like complete, and those value are not automatically used by FSP and just working. There's a backend functions that doing the passing. So we'll cover that in the later slides when we talk about phases. Any questions so far? Yeah. Okay, now we'll walk through a little bit on the FSP phases and then talk about things that need to be done. So FSP temporary mini, this is the phase that's primarily doing caches RAM in it. However, with Skylake, we we don't actually use that phase to do carrying. Coreboot does the cache remediation in itself, and then we'll then call the FSP temporary init for the rest of its settings, because there's some other very early SOC configurations that's in that phase. We don't want to lose that. So the code resides in cache as RAM init, cache as RAM and C file within FSP 1.1 driver. And the code snippet is here. And then there's one critical flag you need to set, which is config skip FSP car. I think with Skylake, there's no option. You have to set that one to yes to be able to use the coreboot implementation of cache as RAM init. And there's two other configs you have to config. One is providing the car base, and the other one is providing the car size that you need.
And those need to match what's in the FSP. So
no, those you set in coreboot, and you pass that to FSP through UPDs.
Okay.
The base and there's two UPDs for the FSP.
Okay.
Yeah. Okay, FSP memory. This is the phase that's primarily doing memory training and the configuration. So the mechanism is prior to calling this phase, coreboot will update its related UPDs. Remember, talk about having options in the chip directory and device tree. So this is where those settings are honored and get utilized. So we look at the ROM stage.c under Skylake. There's a function called SOC memory init params. So that's where the UPDs gets updated with either a hardcore value, like we think, okay, this hardcore is good enough, or it's updated by the config values that we set in device tree.cp file. And also in the ROM stage.c under a specific board directory, there's a similar function called main board memory init params. That's also passing some input to the UPD. For example, if SPD data is passed in that function for the board. Okay, so if you, yeah.
So just on this one, we're hard coding the MMIO size, but we're doing that in a chipset specific location and not in a board location. So can we, I guess we can update that later in the board location if we want a different one?
You have to, if you want to do that, you need to get rid of this line. And then I don't know the sequence of each.
The sequence is that
main board after?
Main board is after, so you can override it.
Okay.
Great,
Okay.
great.
Okay. Yep. If you want to look at the actual caller function for FSP memory init, you can refer to the RAM init.c under FSP 1.1 driver. So that's where you see, all those hooks are callbacks of, are called, and then you actually call into FSP memory function. So the next phase is FSP silicon init. It's primarily doing the rest of the SOC configuration except for the memory controller, and this is supposed to run in RAM stage. The mechanism is actually same. You prior to code interface, the code will update relative UPDs, and then the corresponding configs in the device tree.cb are utilized here. The file is chip.c under SOC Skylake, and the function is SOC init params. It's about doing the same thing. You update UPDs from whatever variable you want. Some are hardcore and some are from your config device tree.cb. And also on the board directory, you have the RAM stage.c that has a similar function to do the main board sitting in params. And I think that's it could be a placeholder. Right now I think it's when we're doing GPL, we're calling GPL configuration in that function for main board. So for the caller function for FSP sitting init, also you can look at FSP 1.1 RAM stage.c, and that's where you actually call into the FSP sitting init with, of course, the parameters. So in terms of integration for those two phases, basically it's all about setting. It's all about having the configuration in chip edge and setting values in device tree.cb, and of course have the lines in respective functions to pass into FSP.
So is there any way to still use the default values from the FSP?
If you don't override in device TCP, you're using the default because the code is actually copy
Right.
the whole structure into and update whatever you want to update.
Okay, but with this right now, is there a way without deleting this that we can use the defaults?
If you have that defined in the chip edge, unless if you don't set in device TCP, you're actually giving 0.
Right.
Right. So that could be a problem. So
Right.
my suggestion is if you have an option in the chip edge, you better initialize it in the device TCP.
Okay.
Otherwise, you could use 0. You're using 0 for all these options.
Right.
That
right.
might be not the default. Right.
Right.
Yeah.
Okay.
So Martin, to use the FSP, you can pass the UPD as a null pointer, and internally FSP can read the defaults and use it.
Oh,
If you don't want this code either, the other option is you can just skip all these things using the configuration.
Okay. Well, just with the FSP 1.0, we specifically made it so that 0 was use the default,
Yes.
which I admit was confusing, but it allowed that option. So I was just wondering, was that removed?
In some cases, I mean, that depends on the parameters of individual policies. But overall, instead of leaning to each specific parameters, we generally said that the function when you pass silicon in the UPD pointer, if you pass a null value, that means bootloader wants the FSP to use the default.
Okay.
So bootloader, I mean, in some scenarios, you don't even need this piece of code to do anything. Right? You can just say pass a null. You already used the static configuration.
Okay.
So it minimizes the bootloader code.
Right.
So Ravi, one question on the hard-coded one is
Yep.
because the ISH enable as an example, right? Is this because different default than what it is there?
It's a choice of platform. I think for Skylake, at least for Chromebook, we don't use ISH at all.
So it's different default.
It's I think FSP default is 1 because the REPs are using that. So we want to change that for Skylake Chromebooks. That could be a problem because there could be other platform out there that you use ISH. So one thing I want to talk about is you might want to ask, hey, I have a I have a board and I need a configuration option, and I don't find that in chip edge. What should I do, right? So the way to do that is you want to look into the FSP UPD VPD.h file as well as the integration guide to see if the option you need is there or not, because UPDs could be long, many, and we don't necessarily put all the UPD in the chip.h file for you to config, right? So if you find the configuration you need in the UPD in the UPD list, perfect. What you do is add to chip.h, configure that in device tree, and add specific lines into respective functions, depends on what phase that UPD belongs to. That's the ideal case. If you don't find the configuration option that's provided by FSP, you want to send a request to Intel, ask for adding.
Gotcha.
Also, the FSP UPD uses the comments in a box format. Integration guide is extracting from the code. So if you're using the code, you already have the documentation. You want to go back to your documentation.
Just another question.
Sure.
Those are very simple examples. So, is there anything, any option you could set that we couldn't do with device tree? Because I'm asking myself, do we really need the mainboard versions of these functions? Couldn't we just take everything from device tree and in the mainboard directory just use device tree and not use any extra functions?
You're talking about whether do we need to have the mainboard functions there?
Yeah.
That's true. Well, actually, in Skylake, the mainboard silicon in params is actually a placeholder, and we don't actually pass in any config values in that function to FSP.
But that would be the only way to override one of these hard
Yeah.
values.
Yeah.
Yeah, but we could just in the SOC directory just if I have code just always use device tree.
Yeah, that's true.
Yeah. But that's the case where one said, hey, for some reason we set a hardcore value in the chip diet in the the SOC file, but you can override that in the main board, right? So next phase is FSP notify. So this phase is registered as a boot state callbacks in coreboot. Currently, there's not input is required for that phase to be successfully executed. There are two callbacks. One is the after PCI enumeration. So this callback is upon this event, I think, this state. This is supposed to call after PCI enumeration, but before execution of third-party code such as options. I'm not very sure how this is enforced in coreboot. But anyway, currently nothing is implemented in FSP for this phase. Basically, call into that and just return without doing nothing. The second callback is ready to boot. It's upon ready to boot. This is supposed to call before you giving control to OS booting. So in this phase, FSP doing things like locking chips registers, or sending the NF post messages to ME. So like finalizing the chipset in the last minute, right, before you put the OS. And no input is required, no integration is required for this phase. And the code resides in FSP util.c under FSP 1.1 driver. You can refer to that code snippet. Okay. So we've just finished walking through the FSP phases. Now I want to talk about a few specific things that we learned from the project. Some are related to FSP integration, some are not. Okay, so SPD data is passed to FSP memory unit, also through UPD. The SPD data connection is coreboot's responsibility. Basically, you either provide a fixed SPD data hex file, or you let coreboot to go and read SPD data from DIMMs through SMBus protocol. But the data connection is coreboot's responsibility. GPL has a big thing. GPL configuration is handled in coreboot entirely and not relying on FSP. FSP does have the capability of program GPLs, but we decided to not use that because we want to have the GPL configuration in coreboot for flexibility. And then for integration, you need to have, for every board, you need to have a GPL setting data file, reside in the board directory. One example is the Google large GPL.h file. For your board, you need to have your a similar file like that. Next one is the video option. VBIOS is no longer used. I think that we starting Braswell, we are already dropping that. So graphics PIM used to be called GOP. It's the new module to initialize graphics. The only input that below the coreboot needs to provide is the vpt.bim file. That's the only file that every board needs to provide. There's one config GOP support. You have to set that one to yes. There's no option. You have to set on the yes to be able to use the graphics PIM, because we drop VBIOS support. And then just functions is in the code resides in vp.c on the FSP 1.1 driver. You can look at it.
So one clarification of the
Yeah.
only for your board is using graphics. If you want to use extended graphics, you still need
That's true. That's true. Yeah.
Yeah, I'm currently replacing VBIOS with something else. So no problem.
So this is just abstractly PA-GOP is just simplifying the code. This is you don't need to go into the dictionary and simplify and get the display out.
Script MP I think we talked a little bit about that yesterday from Gary's presentation. So FSP contains a native MP driver and then service and protocols, but it also provides a UPD called skip MP. So code will utilize that to basically bypass the MP driver from FSP and use Code's own MP driver. The place to set that is, of course, in device tree, and you register that contribution to 1. FSP boot time. Boot time is critical. We always want to make sure that it meet our requirement. So the timestamp logging is already placed around all the FSP phases. For example, if you look at the RAM stage.c under FSP 1.1 driver, we have like before and after FSP silicon init, they're already timestamp added. So once you boot it, you can run cp memory-t, and that you can dump timestamps, and you can see the time consumption of every phases. One example is taken from Google Lars board. So here, if you look at the last line, FSP silicon init, the consumption, the boot time for that is 33 millisecond. So you can use that as a reference for your Skylake board. If you see a way larger number than that, you might have a problem. Something is getting slower. So some issues we found from using FSP. There are quite a few. I won't be able to list all those, but I just pick things off of my mind. FSP size is big. I think on Skylake, the FSP binary release build is 0.5 meg. The debug build, of course, that's not released yet, is a little bit over 1 meg. So that could be a problem because you have FSP copies in the ROM in the RO section, RW and RB. Basically, you have 3 copies of that in your flash. So if size big, you could, and of course you will have ME binary, you'd have microcode and other blobs, and potentially you could you could not fit into the flash chip you have. So that's an issue. We did some optimization to try to reduce the size. FSP boot time could be long, especially at the early phase with the early version of FSP. I could consume like a couple hundred milliseconds or even longer. So we always need to go and then debug and then find the place where it consumes most of the time, and then whether it's some mismatch thing from the sync up, or it's a unnecessary delay, or it's handshake between Kobo and ME gets a problem. So we have to always optimize that to reduce the boot time. I think on Skylake we're okay there. So the other one is FSP is the issue that we found, as Aaron pointed out, and then give solutions. So FSP touches MTRR and doesn't restore its state. I think it's FSP silicon, and does not restore its state to the Kobo setup before calling the FSP phase. So in general, the learning from that is FSP will consume resources, right? But FSP should free those resources and return those resources to the bootloader after it finishes the job, because that's really a bootloader's resources. So I think we take that learnings and then implement that into FSP and going forward. So the other one is also is FSP resets the system from within itself. So this is very bad, right? Bootloader has no idea what has just happened. So one scenario is it destroyed the boot mode from Kobo, and could jeopardize as resume or recovery mode, right? Because you do code reset and then you start from Kobo. So we take the learning there, and then I think from FSP 2.0, FSP will expose the reset request to bootloader instead of blindly performing the reset from itself. So it leaves to the choice to Kobo to make the actions. The other problem we have struggled quite a bit for Skylake is the FSP UVDs are not clearly classified in terms of whether it belongs to FSP memory unit, whether it belongs to FSP silicon unit, right? A lot of stuff are actually in the beginning are put into FSP memory unit. So these were critical when this was particularly critical when the FSP memory unit was not supported by the RW section. You cannot do memory unit rewrapping. So because if you cannot do that, you have all the silicon unit configuration in the memory, you actually cannot update it. You cannot actually do rewrite update, right? So we struggle that, and then I think going forward we are always paying attention to the FSP team, like working with them to make sure, hey, to look at all the UBDs to make sure we have clarifications for all the items, and try to make sure for FSP memory we only have memory related configurations. Because I think the philosophy of ROM stage is just to get the memory up and running, and then provide the memory environment for RAM stage.
And in some cases, we do have more than just one for memory. Few things are like storage, data, or PCI info, because those need to be done sooner than performance and that's why we went to classification.
Yep.
Found some things can be done later. If we have to do earlier, we do see some minor benefits.
Yep. Oh, any question?
So one thing when Robbie mentioned about the size and space optimization, right? In the past, we had a debug is one. And that's one of the benefits in the FSP converter where we get explicitly space one. Since you have three components, you can pick your debug in memory.
Yeah.
Only in the memory of the debug model. So you can just one plus other.
Yeah.
You don't have to take all of the pieces in the debug mode. So that should benefit from the size constraints. You have multiple copies around sometimes.
Right, because with Skylake it's one big pop, so it's either small or big. But with FS2LO, you can choose like each blobs, right? But we still don't release the debug image yet, so that's a.
No, we want to.
Yeah. Right.
Still don't FSP with WinDBK, or is it in new tools now?
You mean
build
with GCC? Yeah.
What do you
We
all?
default use Visual Studio. But if a Chrome user is using the GCC, with NTGO, the size is pretty much comparable now. In the past, like without NTGO and GCC, we had a huge size. Still, we see that the size is the minimum. So we tried all these things so far on this is in some benefit, but we do support all the three components.
Yeah, and then during the FSP integration and all, special thanks to Duncan and Aaron for pointing out a lot of FSP issues and give suggestion directions. So that's okay. This is a picture of the memory mapping with Skylake using FSP, of course. And then if you look at, I'm only listing the stuff below 4 gig. So if you look at from 4 gig downwards, you have the all the different bars and regions, and then you have the PCI Express MMIO space, and then you have the ME memory UMA, and then of course you have the graphics memory DSM and GSM, and the TSEC, and then there are a few new regions that's added with Skylake, the PRM, IoT, PTT. So the toolroom is actually right below TTT, right? So that's where the bootloader, the available memory for bootloader, and then the first region that's been used as FSA bootloader toolroom region is where we put CB memory root in there, and then the very first region after that is actually FSP reserved range, and then the CB memory root actually put ID there and then reserve that region, and then rest of stuff are available memory for system to use. This is just with FSP, you would see those two memory regions there. That's special.
In the 1.0 previous implementations, we had FSP reserved CP memory below, and this one of the discussions with Aaron and so we want the CP memory to be the primary.
Yeah.
So the FSP region is covered under the same. So that's why we added this as an architecture. 1.1 already has this.
Yeah, and then the CB memory top is the function in coreboot that actually, walks through down all this hardware registers to get to the bottom of the toolroom, and use that as the top address for CB memory root. Okay, there's some links. I guess Curious Slide has more links than I do. So FSP download, and then the architect specs for 1.1, 2.0. Okay, so I guess any other questions? That's quite straightforward.
Thank you.
Yeah, thank you.
And after memory, the binary is one piece, is the silicon for the APIs. But that is out.
Oh, there's one there? Okay. Battery doesn't work properly.
Okay, and yeah, you've got VGA as well.
Yeah.
There. There we go, and then
Okay. Is that okay? Can I
yeah,
start?
yep,
Okay. Hi, everyone. I am Hannah Williams, BIOS engineer from Intel, and I work with the Chrome firmware team. And today I am going to talk about the S3 implementation. I'm just going to take the Intel Braswell SoC-based platform as an example. This would actually apply to any SoC, BIOS, OS that is ACPI compliant or supports ACPI. So what exactly is S3 and why is it important today? If you look at the systems today, we need to prolong the life of the battery. So low power modes becomes very important today, and S3 is one of the low power mode. If you look at this vertical block that I have here, the lowest state, those are the system power states that I listed there. And G3 is the system when the system is completely off, where it would draw the least amount of power, and S0 at the top is where it would consume the most power. And the transition from G3 to S0 is the one that has the highest latency. So if you look at all those in between states, the S3, S4, S5, those are all the sleeping states where it would conserve power, and there is varying levels of latency to come back to a completely on state, working state. So when you're in any of these system power states, you can also, if you look at the right, there are the device power states. You can configure the device to be in any of these device power states. So the higher the number, there is higher power savings, but coming back to a working state, how did I do? So coming back to a working state would take longer. And when your system, so from any of these S states, you can control the D states. And then there is also when the processor is idle, when your system is idle, there are these processor power states which can be configured. And again, the higher the number, you get higher power savings. So these are the C state options, and the BIOS provides tables to control any of these states. There's also P states, the performance states, where you can control the processor frequency and voltage. And there's also there's another T state, which actually you can use to throttle the processor frequency. So putting all these things together, you can control system power. So what are the components involved in implementing S3? So there's the BIOS that is involved. In our case, it's coreboot, where the BIOS has to provide ACPI tables, the ASL methods where you can have code snippets which can be run by the OS. And then the BIOS has to enable sleep, it has to enable wake, and it should also handle the wake properly, because otherwise you would go and it would take the same latency as from a off to on state. So when you look at S3 is where the memory contents are preserved, entering into S3 and coming out of S3. So the memory chip itself is not powered off, and it is in self-refresh mode in the case of S3. So it's very important to make sure you don't go back and reinitialize memory when you're coming out of S3. So that's the handle wake part of it. And then if you look through what the OS power management does, the ACPI component subsystem of the OS, it actually needs to check the policy whether S3 is allowed. Usually systems, it depends on the OS as to what events can trigger an entry into S3. So for example, lid close can trigger a S3 entry. So there is all the policy checks whether the mode can be entered into. And then there is this underscore TTS is a method, which ASL method that can be, if needed, provided by the BIOS. So OS calls this transition to sleep, and then it notifies any device driver that has registered. If you go to the third column there, it registered the device PM ops, and the drivers can give the suspend and restore callback in there. So the OS calls us all the suspend callbacks. So it gives an opportunity to the kernel driver now to put the device that it controls into a low power device state. The same thing can also be done using ASL method. We'll go there. And then there is this prepare to sleep method, which is called, it helps to add a port 80 in there, so you know that you're very close to entering sleep from the OS. And the OS needs to save the resume vector because you don't want to reinitialize the kernel on the resume, so the resume vector is important. It also needs to enable wake events because although the system might support many different wake events, there might be a smaller subset which the OS really wants to wake the system out of S3. And then it enters sleep. So the rest of them, so when you enter sleep, the system, the process is kept in reset. So when you resume from reset, it starts from the reset vector. So it goes through coreboot, and then when it enters, again, OSPM context, this wake method is called. And all the drivers, again, get a chance to restore their devices back to the working state. And there's also this final TTS method, which is called, which indicates a transition to the S0 working state. So let's look at the ACPI tables. So ACPI framework as such is, you can think of ACPI as a abstraction layer where a generic OS can talk to a very specific platform. So the OS doesn't know exactly where the hardware registers are, but this framework provides the control for the OS. So if you look at the ACPI tables, the one that is important for S3 is the FADT, the fixed ACPI description table. I've given some file paths here where you can look at the FADT structure in coreboot and in the kernel. That way you can locate where in the kernel it accesses the FADT table. So the FADT table has this FACS, which is where the resume vector is going to be saved. And then there is this system descriptor table where all the device-related information would be in there. So the device specific, there are methods that you can also call, just like the kernel had an opportunity to go and put the device into suspend. There are methods which you can call, which you can provide inside of DSDT, which can be used to control the device power state. So all that is inside that. So these are, the FADT has a pointer to the DSDT and the FACS. And then this is the ACPI hardware register block is the most important thing here, where we can, it actually is, these registers, which are listed on the right side, they are the ones that are used to put the system into sleep. They are the ones that are used to enable different wake events. So, and this is some of them are even the bits, like the PM1, the status and enable form the event block in the ACPI. And so those are basically fixed registers. There are bits inside there which are fixed. And then when an SOC implements these, it can put it in any, it can either be in IO space, memory space, PCI config space. So we give the base address, we can give the which space it is in. For all that is inside this ACPI hardware register block. And that way the OS can go in and write to any of these registers. So there is this PM1A control register, which is the one which is used to enable sleep. And then GPE is the general purpose event register. There's also a few other registers defined in the spec. So to just quickly run through these important ones, the PM1 control register has the sleep type bits, where you can tell, put the system into S3 or put the system into S5. And there's also a bit for sleep enable. There's a bit that can say whether you want a system control event or a system management event to go with any of the events in the system related to power management. And the PM1 status enable is the event, the fixed events. Those, for example, if I take power button enable as an power button as an example, I need to enable that bit in that register so that if my system is in a working state and if a power button is asserted, then it can generate a SCI event. So the OS would then install the handler for the SCI. And if the system was in a sleep state, if it was in S3, then the same power button can be used to wake the system up. So those are all configured in here. And the general purpose events, the bits are not defined in there, so it's up to the SOC to define all the other wake events. Usually the GPIO ones are all in there. And if you look at the ASL methods, some of the ASL methods that are important. So this underscore S3 method is how we tell the OS what to write into the PM1 control register that we saw here. So that value S3 is equal to 5 is actually given in this through this method. So the OS blindly needs to find the offset to that register and write this value in there to put the system into S3. And if we go to the right here, so I just gave an example of a XHCI controller. And this describes this power resources for wake, PRW method, actually tells which bit in the GPE event register can enable wake from this XHCI controller. And then we can also say which is the highest D state we can go to when you're in S3, the device state. And if you are in S3, can a D3 wake the system out of S3? And these are the other methods that I was talking about where you can control device states, the PS0 and PS3. Okay, so like walking through what coreboot does, this is when you're entering S3. So you're in a normal boot scenario first before you enter into S3. So in a regular boot, what coreboot does is it saves the power management registers in cache RAM. So we take a snapshot of the registers coming out of reset and put it in cache RAM. And then we need to clear all the previous state, all the events that were set, the previous control register value, everything is cleared. And what is very important here is the first time we do FSP memory in it, we save all the memory controller register contents, all the initialization. We get that as a hop from FSP, from the FSP. And the first step in ROM stage, we just put that into the CB mem as a first step. And then going into RAM stage, the SMM initialization is important. We need the SMI handler installed in the SMRAM memory space. And we need to enable, what we do in for the Intel SoCs is we enable SMI on a sleep enable. So when we saw that register where the OS sets sleep type and sleep enable, when that happens from the OS, an SMI interrupt is triggered and we enter into SMI handler. So the rest is handled from within coreboot, the SMI handler provided by coreboot. So this is just enabling the sleep SMI to happen. And then we write the MRC data from the CB mem to flash. So we just stash it into flash. And this is very important because in the case of S3, we just need to retrieve the data from there. And walking through what the SMI handler would do when sleep enable is detected is you need to first disable SMI on sleep, because otherwise you'd be re-entering the handler. And then any board-specific enables that need to be done are done from inside there, because you could have GPIOs that you need to enable. And these are all like wake-related functions that need to be called. And then this is one opportunity where you can clear any pending wake, because you don't want to enter when you're trying to go into wake. You don't want any of these events to wake you up from sleep. And so one other thing we did is when you are in sleep, we don't want any power leakage. So we put GPIOs in tri-state, and then this is the invalidate, write back invalidate cache. And finally, we set sleep enable, which puts the SOC into S3. So at this point, the SOC actually asserts a sleep S3 signal. And if you look at what happens is for S3, I just listed some power rails here, but there are a lot more power rails on the system. And in each system power state, there would be a certain number of rails that are on and some would be off. So in our case, especially, we need the memory chip to be powered on. So there is this power management IC that we use, which is very specific to an Intel chip. You can search for the Braswell PMIC data sheet online and see what it does. So there are multiple voltage regulators inside it. And there is this handshake with the SOC where SOC knows when the power rails are stable. So the power OK goes from the PMIC to the SOC. So there is handshake, and then there are the voltage rails that can be turned on and off through that handshake. So this is how some of the rails will be turned off in S3. So now that we are in S3, even before we entered S3, we should have enabled wake. So if you look at some of the examples of what can enable wake your system up, it could be like clicking on your mouse, hitting on your keyboard, lid open. It could be RTC alarm. So whichever one your system supports, it should have been enabled prior to entering into sleep. So those GPE registers have bits that enable the wake. So what the OS does is it goes through these PRW methods, and before you enter sleep, it'll go and set all the enables. So assuming one of the wake events that we enabled has triggered the SOC to come out of wake. So let's walk through the flow in the coreboot side. So we need to know what state we are coming out of. So the power management registers that we usually cache very early on in ROM stage will tell me whether I'm coming out of S0, S5, or S3 state. So that's the previous sleep state. And once I know that my previous sleep state was S3, I should make sure that I do not call the complete memory initialization. So there is a boot mode that we tell to FSP memory in it that we are coming out of S3. And then we also pass the entire cached MRC data related to the memory controller in this pointer, this NBS buffer pointer to the FSP. And then there is this ROM stage handoff block that you'll see in coreboot that gets created. And in RAM stage, we use that handoff block to know whether you're in S3 resume or not. And then instead of loading RAM stage from SPY Flash, we would just use the cached memory data to start the RAM stage. And then all the device initialization would happen just as it would in any other case. We go through the entire device enumeration, configuration, initialization. And after the device initialization is when, again, we need to decide whether we need to load the bootloader or do we need to resume. If we need to look for the FACS from the FADT table, we need to find the FACS which has the wake vector. So if the wake vector exists, then we jump to that. Otherwise, we would go through the path of loading the bootloader, which would in turn load the kernel. And since we clear all the power management registers, the OS will not know what was the source of wake. So there's another method which gives the wake source to the OS. So this is SWS method. And these are the FSP memory in it, the boot mode that I was talking about. So that's the boot on S3, or boot with full configuration is when you start up power up the first time, and then there's a fast boot case. And you can look at all these config flags if you're starting on a new implementation of S3. You can look for these config flags in one of our existing implementation to start with. With respect to debugging, the most important thing first is to make sure that your ACPI tables exist in the OS. So look for that first, and then you can use the IASL. You can retrieve those binaries, the table binaries, and then use IASL, the decode option or disassemble option, to extract the table. So you'll now see it as a ASL again, and you can look for the missing ones in there. So to check whether your S3 support is available in the OS, you can do this cat sys power state. And if you see mem, that means the OS now knows that it has the necessary information from the BIOS. And to enter S3, we do a echo mem to sys power state. I have some references here. The ACPI spec is the most important here. Okay, that's it. Any questions, anybody? Yes.
You mentioned that you put some GPI also to tree state in SMM.
Yes.
So why is it done in SMM?
Why? Because that's how we get control. In all other cases, it's in a working state, right? But just before you go to sleep, because that GPR might be used prior to that.
So doing it in ACPI is too early.
You're saying if I put it in some of the ACPI tables, we could. Means we could put it in one of the tables that gets called very close to this point. Yeah, we could do it there too. That's an option.
Just the SMM handlers are available, and so it's easier to do it there.
I was just looking at the SMM handler, and it looks pretty generic, but for this one, it is possible.
Yeah.
Yeah, I think it's just because it was available.
Yeah, we could put it in the ASL though. We can do anything from in there. We want to do it as close to sleep as possible, so we don't affect the functionality of that device. Yeah.
Okay.
Yes.
You mentioned that EPM block could move around. Is that something that you reserve the right to do in the future, or is that something that happens a lot?
Actually, maybe Duncan or somebody who knows ACPI better can help with this, but I know there is the space ID bit, right, where we can say whether this base address is in IO space or config space. But does that apply to the PM1 block today? I'm not sure. Because there is, if you look at the structure, if we have time, I can show that quickly.
If we've got a break after this, so I mean,
Okay,
take as much time as you want.
okay. Let me show you the structure of FADT. Where am I? I'm in depth charge. Okay, so this is the FADT structure. So if you look at this definition, this structure definition, which is the PM1, this is that extended event block structure that has a space ID in it. So which is the one which is used to say whether you're an IO space or not. So we actually need to go into the kernel to see whether it uses this space ID or not to access the PM1 registers. Yeah. Okay,
All right, well, thank you very much.
thank you.
All right, and we've got a half an hour break before the next presentation. And I think Linksys is actually going to give the next presentation over in the other room. So